Okay, so let's start on the new material. So this is chapter 8. So we have Exergy, okay? So we've dealt with energy, this is Exergy, okay? So, or availability is what other books will call this. And it is basically your, let's not use useful. Let's say work potential, okay? All right, so within this, we're going to talk about, basically we're bringing in the second law of thermo, okay, into the performance. So we've really, with performance, done more with the first law, with energy. Okay, here we're going to integrate energy and entropy into a performance metric of Exergy. Okay, so Exergy, it kind of looks at what's the maximum useful work, or the work potential maximum. Okay, so from any fluid or device, you can figure out the work potential. Okay, reversible work, okay, we'll define that. It's that maximum useful work between the two states, okay, for a process. So state 1 and state 2, not state 1 and state 2s like we had in chapter 7 for an isentropic process. It's between state 1 and state 2. If you reversibly go between those two, what's the work that you've got to get out, or what work would you have to put in? Okay, we bring up extra destruction, or that's basically like wasted work, okay, during a process. We define the second law of efficiency in this. So we've talked about like thermal efficiency, it's just ratio of energies, or efficiency, desired output or required input. That's looking at ratios of energies, but we're not bringing in the second law when we look at that and the limitations we have because of SGen with entropy generated. Or think about a heat engine. You have Carnot being your maximum. You can't go above Carnot's efficiency, so you're not limited of 100% thermal efficiency in a heat engine. You're limited by the efficiency of the Carnot. So the second law of efficiency brings that in, okay? And then, not to be outdone by the conservation energy or the entropy balance, we have an Exergy balance now to see the work potential flow, okay? And we'll do that in a closed system and open system, okay? All right, so Exergy, the work potential of energy, okay? So Exergy, or availability, as I said, or available energy is another one. What's really important to understand with it is it deals with the dead state, okay? The system is in equilibrium if it's the same as the dead state. So the dead state is kind of like the environment, okay? So that defines our dead state. This T naught and P naught, that is our dead state. So we have a temperature of 25 degrees Celsius, 101 kPa, and we end up having in this tank, air is 25 and pressure is 101, and we have no kinetic energy, so no velocity or height, so no potential energy also. So this and is the same as the dead state, so there's no work potential, so no Exergy. Now if that tank had a higher pressure or lower pressure than atmospheric, or higher temperature or lower temperature than the environment, now you have a potential to do work because you have that difference between what's in the tank and the environment. All right, so here just talks about some of this again. The other thing, though, in this one is the if you think of the atmosphere, all right, that's what's being shown in the picture. It has a ton of energy, but there's no Exergy, okay, because there's no difference to work with when you're talking about the atmosphere. There's no potential to do work. You're at the environment. There's nowhere to expand through a turbine or something if you're already there. If you're already at the environment's value. All right, so now defining the work potential, or Exergy, okay, for kinetic and potential energy. So these ones are nice and easy. This should be potential energy here. All right? They have them labeled backwards, right? And this should be kinetic energy here. Okay. And this X is what we'll use to define Exergy. All right, so we have the Exergy from kinetic, Exergy from potential, and it's the same. Okay, so potential energy G times your height, or velocity squared over 2 for your per unit mass kinetic energy. Okay, so those are nice and easy because they're the same of what we've dealt with energy. So you can convert all that value to work. So, and you see that here with this, hydrodynamic turbine. Because of the potential energy, we can get all that. That is our max that we can get out of that potential energy. But there is if we think of energy, the easiest one to think of is even a reversible heat engine. The best heat engine we can achieve, the Carnot, the reversible heat engine, where all the processes are reversible. If we had all that energy and put it through in heat, and we put it through a reversible heat engine, we'd only get some of that out as work, all right? The other we have to reject. As the Kelvin Planck statement says, we have to reject some heat. So that part of the pie is unavailable energy. Right? So our work potential is actually just this amount of that energy. Our Exergy, or work potential, is the work we would get out of that heat that we have, that we put through that heat engine. So that's the difference between the energy and the Exergy. Okay. All right, so going through another term, we have reversible work and irreversibility. So going through some of the things that are being shown here, we'll start off right here. We have useful work. Okay, useful work is the work that we've dealt with the first law in the conservation energy, minus any work we would have to do on the surroundings. Okay, so what do I mean by that? Well, you see that here. Okay, the piston is moving up. Well, it has to push the surroundings to do that because the surroundings are at a pressure. So the piston is this air, by expanding, is pushing the atmospheric air. So we're doing work on the surroundings, and that's just something we have to do because we have surroundings, right? So that work is not Exergy work potential. That's just work we have to do. So we have to subtract that off our work, and that's what becomes the useful work. Okay. All right, so the work on the surrounding is just the atmospheric pressure and the change in volume. Okay. Now, if what you see down here, now if there's no piston moving, so we have a rigid tank right here, then there's no work we're going to do on the surroundings because the volume's not changing. We're not pushing the surroundings, so the useful work is actually just the same work that we've dealt with before. Or we have a steady flow device, the walls are fixed, so we have the useful work is equal to the work of that turbine, let's say. And an example, if we were blowing up a balloon, we'd be pushing the atmospheric air out. Okay. All right, so, yeah.
Can you explain what W is again in the work useful equation?
Work, W is just work, and then the subscripts tell you, oh, this W. This is the work that we've dealt with in the past. So that's just the first law's work, any of those. So we're just changing the work we've dealt with in conservation energy to the useful work, okay? So if we have to push surrounding air out, we subtract it off. Or down here, if we don't have to push the surrounding work off, we don't have to subtract it off, then the work useful is equal to just the work from the first law, okay?
Yep, thank you.
Yep. All right, so then we can talk here is a reversible work. So if we have state 1 here, and we have state 2 here, and we have our process path that's doing this reversibly from 1 to 2, we have a reversible work from that, okay? Now our useful work, our actual work process, is going to be this one. It has dashes, but it's going to be less because we're in this case, we're doing a workout, okay? So we're gonna get more work out of the reversible process, okay? And the irreversibility is just gonna be the reversible minus the useful, okay? Or in this case, you can see it here. We have the two being shown here. This one is out, so that would be for like a turbine. So if you're putting work out from state 1 to 2, you're going to work out, your reversible is going to get more useful, the actual basically useful one is going to get less, and your irreversibility is going to be the difference, the wasted work potential. If you're putting work in, so you'd have maybe a compressor or a pump, so then the reversible one is going to be less, right? What you're going to actually put in, and the useful one is going to be more, and your wasted work potential is the difference. Okay. All right, so here's an example of the rate of irreversibility from a heat engine. Okay, so we have our heat engine. They gave us the work they're getting actually out, the heat we're putting in. We have the source temperature, source sink, right? And then we're going to create this equation right here. As we know, the thermal efficiency is work net out over Q in, right? So if we want work net out, we just have thermal efficiency minus or times the Q in, right? Well, now if it's reversible, the most we can get out, we have an equation for the thermal efficiency of that, and that's where we have our 1 minus TL over TH, the reversible heat engine times Q dot in, right? So now we've basically derived our equation right here. So we substitute in our values that are given of the source, the TH, and the sink's TL, and we get that the reversible work out should be 375 kilowatts, right? We're actually getting 180, right? So if we subtract 375 from 180, our rate of irreversibility, or our wasted work, is 195 kilowatts. All right, so second law efficiencies. All these ones are kind of the simpler ones of showing, you know, as I mentioned earlier, if we know Carnot is our limiting, right? That's Carnot, our reversible thermal efficiency for a heat engine. Then we would just take our efficiency and divide it by that. So now we have our maximum is 100% when we do that, because we're looking at our thermal efficiency to the reversible case. Or down here, refrigerator and heat pump, same idea, where we have the actual COP over the reversible, because when we calculate a COP, it could be 1, 15, right? So what does that mean on what you can achieve? Well, you can achieve a maximum of the reversible one. So divide it by the reversible. Now you have how close you are to the reversible. So here you see an example of thermal efficiency of this 2 heat engines. They both have 30%, right? But the Carnot, the reversible heat engine value is different because our source temperatures are different. So we have 50% and 70%. So if we do the thermal efficiency, second law thermal efficiency over here, we're going to get 30 divided by 70. And this one is 30 divided by 50. So if we're looking at it and how good we're getting to that second law efficiency, we see that this heat engine is doing a better job of getting work out of that system than this one. Okay. All right, so then these other two are just that work producing, work consuming. Work producing again is a turbine, right? Work consuming is the compressor or pump. All right, so turbine, reversible is going to get you the most work out. Useful, what you're actually doing is going to be less. So you're just comparing those two to get how well your second law is efficiency. And then here you're just switching because with compressor and pump, you're putting in work. So the reversible is going to be less, okay, and your actual is going to be more, okay. All right, here's an example of a second law efficiency of 100%. Your thermal efficiency is 70, the reversible 70. Second law efficiency is going to show you're doing the best you can, 100%. All right, general definition of the second law efficiencies, and the ones I just showed you on this slide could all be derived from this general law, is exergy recovered, okay, divided by exergy expended. All right, so, and then if we rearrange, we can do 1 minus exergy destroyed over exergy expended, because if we have exergy recovered minus exergy, let's do it the other way. Exergy expended minus exergy recovered. We're going to get exergy destroyed. And that's how this part of the equation comes from, is this one. So if we substitute, rearrange this equation for exergy recovered and plug it in here, we'll get this one, okay? So what's expended is kind of the exergy you're putting in. Recovered is kind of the exergy you're getting out. You can also get a second law efficiency of 0, right? If all the exergy you're expending is going to destroyed, you're not recovering any exergy, you would have a 0 second law efficiency. All right, here's a derivation, and what this is, when we deal with the COE, especially closed system, inside our system, the energy inside our system is that change in internal kinetic potential. Well, we need to figure out for a system, in this case, it's a closed system right here in this piston, what's the exergy change inside that system, okay? What's the work potential inside that system, okay? So we need to derive and figure out where that comes from, okay? We have this delta E for our closed system. For entropy balance, we have delta S, we have the change in entropy inside our system. So now we need to figure out the change in exergy, okay? All right, so we'll start with looking at that piston. We have conservation energy, started on that boundary I set up. And out of it, we get some work, we can get some heat, okay? Now we need to figure out equations for the heat and work that tell us what the exergy is, okay? So if we go out of the piston right here and start looking at this work, all right, it's boundary work, okay? The piston's expanding, so it's PDV, okay, but we're pushing on the surroundings. So we're doing work on the surroundings, okay? So this first part would be the useful work we're getting out, because it's the pressure minus any pressure on the atmosphere. And then this part is the atmospheric pressure times the volume we're changing. So that's the work we're pushing on the surroundings that we just have to do. So this part right here is going to be our useful work, okay? So that's that piston moving is getting that amount of useful work, okay? So we have a relationship with this and these two terms for the work right here and relating it to what that useful work or exergy is, okay? Now we need to work on this heat transfer term right here. Okay, so if we look at now the heat engine, because we have heat there, but we want work. So we need to figure out the useful work off of that heat. And we already used that. And that's from using the thermal efficiency of the reversible times the Q, that heat. So we would get that amount of work out of that reversible heat engine. Okay. Well, let's just move some stuff around. So multiply the Q out. So we have this equation. We can also get rid of this dQ over T, because this T is this temperature inside the system, and we're taking the temperature of that fluid and pressure and bringing it to the dead state. We're saying, what's the work potential, right? What's that work potential of that pressure and temperature to the dead state, okay? So this temperature is changing to the dead state temperature, so that's not so easy to use dQ over T if the temperature is varying. So we can instead substitute in dQ over T as the change in entropy, defined in chapter 7, okay? So now we have a relationship for this in these terms. If we rearrange it for heat transfer on the left, and then the work out of the heat engine, and then this T ds on the right. So now we have an equation also for heat transfer. So we already set up one for the heat, or for the work here. Now we have one for the heat transfer. So we plug those into our COE that we started with for dQ and dW, okay? And this is what we get. If we plug those in and just leave the works on the left-hand side, because that's the useful work we get out, okay? The work potential on the left and all the other things on the right-hand side. And you see all the other things on the right-hand side are properties, okay? Changes in properties. So that ends up being our exergy of that fluid inside that piston cylinder device. So that's where we just change this to capital X, right? Lowercase x is per unit mass exergy, capital X is the exergy, okay? So if we take it to the dead state, we have change in internal energy to the dead state, the work we're doing on the surroundings basically, and then our T naught delta S. Again, this is the dead state's volume, dead state entropy, dead state internal energy, and then we also have kinetic and potential. Okay. So that defines the exergy inside a closed system. Here is, we're just taking that capital X, right? If we divide it by mass, we get our per unit mass exergy of our closed system right here, okay? If we instead here do the exergy change from state 1 to state 2, here was just the exergy. If you have the exergy at state 1, what's that value? The exergy at state 2, what's that value? Here's the change, okay? So instead we have x2 minus x1. Well, what's nice about this is it gets rid of a lot of terms. If you solve for the exergy at state 1 and the exergy at state 2, and then subtracted them, you'd have to get all these dead state values here, here, and here for the properties. Well, when you take x2 minus x1 of exergy and put it together, those things cancel, and you just have state 1 and 2's internal energies and volumes and entropies. Okay, so it's easier, less kind of any lookups or dealing with the properties. Here's the per unit mass of the change. Okay, so just dividing this above by mass, we get this. Okay, so I recommend using this whenever you can, okay, and not this one, just because it's quicker. All right, so that's of a closed systems exergy, right? Closed system, okay? So now we need to know, like we have internal energy for a closed system, and then we have enthalpy for that open system with flowing in and out. So now we need to know exergy of a flow stream. So we need the flow exergy, okay? And that comes from just knowing that if you think of back to what is enthalpy, it's internal energy plus the flow energy, right? So we just need to figure out what that Exergy is from the flow energy. Okay, so we basically have here the flow energy, and then we subtract any work we would have to do on the surroundings, because our pressure includes that pressure that we would be pushing the surroundings out. Okay, so we just combine those two, and we have this. Okay, now we put that to figure out our flow Exergy. We take our non-flow Exergy that we just defined right here in this slide and add our flow Exergy. So we're just adding this term right here. And then if we start moving things around, we can combine internal energy and these flow Exergy terms together, and we get enthalpy instead, right? And then we still have the temperature, dead state temperature delta S, kinetic, and potential there, okay? So this is then the flow Exergy. So that simplification just ends up being flow Exergy right there. So that's what mass flow rate would carry in or out in an open system. Here's the change. So again, if you can set up the change, it ends up being a little less properties you have to deal with, because you're not, dead states go away. You just have state 1, 2, 1, 2, 1 and 2, 1 and 2, okay, for the change in flow Exergy. All right, so here's the nice slide that simplifies all the stuff we just did. We have our closed system. So it's a fixed mass system, closed system. We have the energy inside that closed system right inside there. Right inside, we have our energy, which is internal energy, kinetic, potential. And then we have that flow Exergy, that work potential of that fluid inside that boundary. You know, if we have our flow stream, so let's say we have state 1 flowing into a boundary, okay? We have the energy that the mass flow rate's carrying in or out, and then we have the Exergy, the work potential that the mass flow rate's carrying in or out, okay? All right, so some of these with an example. We have pressures 1 megapascals, temperatures 300 degrees Celsius. And the dead state, which is the surroundings, is also at 300 Kelvin. Okay, let's make that a little better. Okay. Well, we set up the Exergy inside our system. Okay, so the Exergy at state 1, we have mass times the per unit mass Exergy of a non-flowing fluid. So we just grab, it's basically grabbing this equation at the top here. Okay, well, there's no kinetic energy, potential energy, so that goes away. This ends up going away because we have an ideal gas, so it's compressed air, right? And delta U is CV delta T, right? Well, if we have an ideal gas and it's CV delta T, this is T1 minus T naught. Well, these both happen to be the same temperature, right? T1 and T is surroundings. So there's no work potential because the temperatures are the same, and it's an ideal gas. But if it could potentially, if it was water or refrigerant, it's enthalpy or internal energy, which those can change because of the latent energy, right? But because we have an ideal gas and it's changing internal energy, this goes to 0. Okay, so we're just left with these two terms and the mass flow rate for the Exergy or work potential inside that piston cylinder device. Okay. All right, now we have a compressor. So we take our boundary here. We have state 2 exiting. We have state 1 entering, right? They just want the exergy change during a compression process. So it's an open system. So exergy at state 1, exergy at state 2. Okay, so the exergy change, so it's 2 minus 1, and we just look at the flow exergy. Okay, so we have a flowing fluid, so now it's the flow exergy term. So we have that equation that we derived right there from the inlet to the outlet. Well, we can neglect and say the kinetic energy change from 1 to 2 is not much. Potential energy is not there, so we get left with the enthalpy and then our temperature, dead state temperature, and the change in entropy. All right, so that deals with the exergy of a non-flowing fluid and a flowing fluid. We have exergy by heat transfer, which we kind of already used in our derivation. So capital X for exergy, right? And then it's heat transfer. We have our equation that we used with the thermal efficiency of a reversible heat engine times that Q. And that's the work potential we can get out of that heat transfer. All right, so here's an example of it with a wall, a brick wall here, of looking at heat transfer, entropy, and exergy all at the same time. Well, if we think of the temperature, the wall's got insulating properties, so say we're trying to keep heat in on 1, so it's going to drop, and we have a lower temperature 2, okay, or we're air conditioning space 2, right? Well, conservation energy just says Q is Q, right? On 1 to 2, it's the same amount of heat transfer. Conservation energy, there's no work, so heat in is heat out in this case. Now, if we look at entropy transfer, well, by entropy by heat is Q over T, right? While the temperature changes from T1 to T2. So T1 is higher, so when you divide T1 by Q, you're going to lower entropy. And when you divide T2, because it's smaller, you divide Q by T2, you're going to get this higher entropy. So the difference between those two is your entropy generated. Okay. Now we look at exergy transfer. We use our equation that we just showed here. Okay, we use it at state 1 and then at state 2. Again, the temperatures change. So 1 is a higher temperature, so you're going to have more exergy or work potential. And then as the temperature drops, you get less work potential, okay, or less exergy. So the difference is going to be your exergy destroyed. All right, so, and we showed this a little earlier, again, exergy by work. So again, exergy and then work is for something with boundary work. We have our typical work from the first law. We got to subtract off the surroundings. Any other types of devices, right? We don't have to worry about subtracting off the work we're doing on the surroundings. Okay, and this is the work of the surroundings. Mass flow rate, so exergy transfer by mass. So mass just carries in your flow exergy. So right, if you have a system like down here, mass flow rate's carrying in enthalpy, entropy, and now exergy. All right, so then let's talk about that destruction of exergy that we had here. Okay, we'll set up an equation to define it. Okay, and that's where the decrease of exergy principle or exergy destruction comes from. Okay, so we have an isolated system we're going to define on. Isolated system's a really big boundary, right? So then heat and work, there's none of it. Okay, it's inside our boundary, so there's nothing crossing our boundary in the form of heat, work, mass transfer. So if we set up that big boundary, then there's no energy going in or out, no entropy going in or out because heat transfer is inside our boundary, no mass transfer. So then we just have the change in energy of our system, and then we have Sgen is equal to the change in entropy of our isolated system. Okay, well, we can combine those. Okay, so we combine the two, but we do it first by multiplying second equation by T naught, okay, and then subtract it from it. So if we do that, multiply it times T naught, and then subtract it, that's the entropy balance that we derive from the energy balance. Okay, we get that equation, okay? All right, so that, we see Sgen in there, we see change in energy, we see this T naught delta S. All right, so what does that mean? Well, let's start with what we were ready to find, the non-flowing Exergy equation that we defined earlier. So change in Exergy from state 2 to state 1 for an isolated system is just change in non-flowing Exergy. We go grab that equation, or the change in energy, pressure of the dead state times the change in volume, temperature of the dead state times the change in entropy. Well, the volume's not changing, so that term cancels. So we're just left with the change in energy and then the dead state temperature change in S. Well, if we look at that, that's the same as what we have on the right from above. Okay, so that is the same as that. Okay, that's all my arrows. So then we can just substitute in Exergy for that. Okay, so we do that and we see it here. All right, so that means we have T naught times Sgen and then this subtraction, and then that's this change in Exergy. Well, we know stuff about Sgen, right? We know entropy generated has to be 0 if it's reversible, right? And then positive for an actual system. It can't be negative. Okay, so if this Sgen can only be a positive or 0, right? T naught is absolute temperature, so that can only be a positive value. It can't go negative when you're dealing with absolute. So you have basically a positive times a positive, and then you have this negative, which switches it to negative. Or you can have 0 here, right? Because if Sgen is 0, it makes it all 0. So that means this x2 minus x1 has to be less than or equal to 0. Okay? So that is our decrease of Exergy principle. Okay? We've also defined what X destroyed is then. We got rid of that minus sign in this definition. So T naught times Sgen is our Exergy destroyed. So just by putting the dead state temperature on and multiplying it times the entropy generated, we've created the wasted work potential, the lost work, or the irreversibility. So we've taken that Sgen term, which we just kind of had a value from chapter 7, and put a meaning to it in the term of work or irreversibility, right? So now that quantity makes a lot more sense than that kilowatt per Kelvin or kilojoules per kilogram Kelvin. All right, so that means with this setup, T naught times Sgen, then minus isn't in this equation. We have a positive, and then Sgen has to be positive or 0. So that tells us irreversible process, reversible, impossible, okay? And just like entropy in Exergy, if your boundary is it's not an isolated system. So in this case, it's just this fluid inside the piston. So we do have heat transfer. Then the change in Exergy system can be negative, but because of that heat transfer, you still get an X destroyed that's positive. Okay, it offsets it. All right, so let's put all this together and create a Exergy balance. Okay, so we have a closed system. Let's first set up our system. It's this nice circle, right? We can have with mass, heat, work going in. We can have mass, heat, work going out, although it's a closed system, so we can't really have mass, but we're generalizing for now. If we just set it up in words, we can have what's crossing our boundary on the left. On the right, we have inside our boundaries change in Exergy. And then we have what's being destroyed. That's that T naught Sgen. Okay, so now we put it into variable forms. This is what's crossing our boundary, x in minus x out. the change in exergy inside our system, and then the exergy destroyed. Okay, and then rate form, we're just changing it, dividing by delta t, and then making that go to limit, go to 0. So then we have our exergy for non-rate form and rate form, and then here they're just showing you all the different parts of the exergy, right? Is with mass flow rate, work, heat, destroyed, with non-rate and rate form. We can also do a per unit mass basis, so we could just divide this, the general form by mass, and we get this lowercase x for exergy, or we could divide this by mass flow rate, the rate form, and we get, again, this one, the per unit mass basis, just like we did that sometimes in Thermal 1 with the conservation energy. All right, so now we start substituting in. So we take this general form we have here, or the rate general form, and we start substituting in our different components. So for a closed system, there's no exergy from mass, so we just have heat and work, and we have the destroyed, which here's that negative sign back for the T naught esgen, and then we have the change in exergy inside our system. So we have heat and work crossing our boundary, or X destroyed, and our exergy change inside our system. So here we have the heat right there. Here we have exergy transfer by work. Right there. We have then our X destroyed right here, okay, and then our change in exergy right there, okay. And then rate form, we're just adding that dot to our heat transfer, to the work, and then we've taken V and made it dV dt. So that means it would be an expanding system with respect to time, so like blowing up a balloon or something like that. But most of these, this term right here goes to 0. You still have this term. Okay, when you're in rate, a lot of those go to 0. All right. Steady state, we still can make that 0. Okay, if it's steady state. Again, this heat transfer, right, or temperature goes with this heat transfer. So that's the temperature at which that heat transfer is crossing your boundary. All right, so here we have a closed system of a brick wall again. So this first one is the exergy destroyed through the brick wall. So our boundary is just brick wall. So that's temperature right there, and that's the temperature right there on the brick wall. Okay, so we have our exergy balance in its rate form, because we're looking at the rate of heat transfer through it. It's steady state. Okay, so we have exergy in and out. Well, there's no work, no mass transfer, so we just have heat. Okay, so exergy work, exergy in, exergy out from heat transfer. And the big is the temperatures. Okay, using the temperature on each side of the wall. Solve for X destroyed, we get 52 watts, right? If we extend this to inside and out of the wall, now you have 27 out here in the air and 0 all the way in the air on the other side. So now we just change what those temperatures are, okay? So if you take it from those temperature boundaries from all the way outside and inside the wall, not just through the wall, we get 93.2 watts of exergy destroyed from this heat conduction. All right, there's a few things going on in this one, because it's starting to incorporate a couple other equations that we've already know, the conservation energy down here in the bottom right, and entropy balance. But we'll start with, we have some heat transfer going on, and the piston's moving up, right? So if we set up a boundary that's a little bigger, so we have our extended boundary. Okay, we do our exergy balance for it. Well, we have Exergy by work, because there's work, the piston's moving. There's exergy destroyed. We have change in exergy inside our system, but we happen to cancel off the exergy by heat transfer. Well, that comes from that exergy by heat transfer is this, right? It's Q, and then this is the temperature that goes with that Q. Well, if we made our boundary extended right here, that is T naught also. That is the temperature of the surroundings with that extended boundary. So that means this becomes T naught. So that's 1 minus 1, which is 0. So there's no work potential then if the temperature, there's no difference in temperature for that heat transfer to drive, say, heat engine between those two temperatures. Okay, so now there's no work potential from heat transfer with this case. Okay, so then you just need to get X destroyed. You would just need to solve for the change in exergy inside the system, and then your useful work, and that's what's right here. So we have change in exergy. So inside the system, just grab that equation for the non-flowing exergy that we had earlier. And then the useful work is the work minus the work we have to do on the surroundings, because it's a piston and it's pushing the surroundings out. Okay, so we have then the boundary work we would get minus the work on the surroundings. Okay, so we have our boundary work and minus the work on the surroundings. Okay. All right, so we don't know the boundary work, so that's where we could go into our concept, our COE for our actual boundary work. Okay, so we have heat transfer in this, boundary work, delta U, rearrange, and we get an equation for the boundary work, right? All right. The other thing we could do to get X destroyed is we did the exergy balance up here, but we can actually just do the entropy balance, because X destroyed is just T naught times S gen. Well, to solve S gen, we just do the entropy balance of a closed system. And that ends up being this from the entropy balance in this case. I didn't show all the steps, but that's from the entropy balance. This method to get X destroyed is the quickest. Okay, you saw all the steps we had to do for the exergy balance. If we want to get X destroyed, the bottom left entropy balance is always the quickest. There's less steps. Okay, so I'd suggest that. The entropy balance is good, or the exergy balance is good for other things. Okay, it's not that it's not good for anything. We just use this all the time. But if you just want X destroyed, this is the best way to go about it. Okay. Now, if we bring back the second law of efficiency, that's exergy expended divided, or exergy recovered divided by expended. Well, the simplest way to look at this is the exergy balance, right? If we want to do second law efficiency, let me erase all my scribblings over here because this is the good part for it. All right, so we have no heat transfer, right? So that's nothing there. But we have exergy by work, we have X destroyed, and we have the change in exergy of our system. Well, that's our three things. We're getting work out, so that's going to be our recovered in this case, because the work's out. So that's our recovered. We got destroyed, which is the difference between recovered and expended. And then this is changing work potential. It's dropping in work potential. So this is the expended. Okay, so you can just kind of think about it from the direction of those exergies. That exergy is out, so that's recovered for work. Expended is it's dropping, it's negative, so it's our expended. Okay, and destroyed is the difference. Okay, we could also use 1 minus X destroyed over X1 minus X2. Just bringing in that X destroyed is exergy expended minus recovered. That equation back from the earlier slide. All right, here's another example. This case, we have a gas of air, and we're putting in some paddle wheel work, and it's raising the temperature to 130 degrees Celsius. We have our dead state temperature of 70. So we're putting in this paddle wheel work and raising T1 from 70 to 130, okay? And we have an initial pressure. So if we do our COE, it shows right here, there's no heat transfers. This is well insulated, okay? So there's no heat transfer, and we're just putting in work. There's no boundary work. It's not expanding or contracting. So we just have delta U, which we can get this, and that's 20.6. If we do our entropy balance, again, there's no heat transfer, so Q over T plus S gen for our closed system, delta S, that goes no heat transfer, so S gen is just equal to delta S, right? So then for X destroyed, it's T naught times that S gen, so we have T naught, and then this is our delta S. So we just go to the ideal gas law and look at, for calculating the change in entropy of an ideal gas, we have this equation. It's simplified a little bit because there's the plus R ln V2 of V1, and just like we did in one of the examples last week, it's a fixed, the volume's not changing, so natural log of 1 is 0. So they've simplified that to write this, okay? But anyways, that X destroyed is then 19.6 BTUs. Okay. So out of 20.6, we're destroying 19.6 BTUs. So 19.6 is a wasted work potential. So if we looked at it a different way, what would be the reversible process for raising this temperature? So again, we're going from T1 to T2 with work, okay? With work. So now if we were to do this process reversibly, so okay, so this is more an exercise in what it could be. So if we're doing it reversibly, then it's actually 0, okay? So we're not doing the paddle wheel method, we're doing it different, but reversibly, okay? So that makes X destroyed 0. We have the change in exergy of our system. So we're only putting in work, but now we're doing it reversibly because X destroyed is 0. So we have the change in exergy of our closed system. Plug what the change in exergy is, simplify for delta U and delta S, and we get 1 BTU. Okay, so the reversible work. So if we were to raise from T1 to T2, reversibly with reversible work, it should only take 1 BTU. Okay, and you can see that by subtracting work reversible in is this work, the paddle wheel, minus X destroyed. Okay, because that's the equation earlier on. That's that useful work minus work reversible in, okay? So it all ends up being related, okay? So how would we actually do that reversible work and get 1 BTU to raise the temperature from 70 to 130? It's using a reversible heat pump, okay? If we use a reversible heat pump, we would only have to put in 1 BTU of work to put in that 20.6 BTUs of energy to raise the temperature of the air from 70 to 130, okay? So that's our best. So that's where you get like a hot water system that runs on a heat pump. Well, that's better than an electric resistance heater for efficiency purposes. Check time. Still got a few minutes. All right, so if we, in this case, drop some iron Actually, yeah, I'll just do this one. Drop some iron into the water. Okay, so we have water and we have iron. We have the temperature of the iron, 350 Celsius, 5 kilograms. We have the water's 30 and 100 kilograms. If we do our boundary around the whole thing, okay, and we say the tank is well insulated, okay, then our boundary includes both the water and the iron. Okay, there's no work crossing our boundary, no heat, so that goes to zero, and so energy in and energy out. We just have change in energy inside the system. So we have delta U, there's no kinetic, no potential. So we have delta U of the iron, so the change in microscopic energies of the iron plus the change in microscopic energy of the water. Okay, they're both at this conditions incompressible substances, so we substitute in our equation for delta U for an incompressible substance of iron and water. Now, if we did the Exergy balance for dropping this iron block in the water, again, closed system, boundaries, the whole thing, there's no heat and work crossing our boundary, so there's no Exergy going in and out of our boundary. We still have X destroyed, we still have Exergy change inside our system. So we would just have X destroyed as a change in Exergy, the non-flow Exergy inside our system. And that you could also do the delta X of the iron plus the delta of the X of the water. Okay, just like we separated internal energy, we can do that with Exergy, just like we would do that. We could do that with entropy and separate the change of one substance and then the other. All right, so we got a few more slides, but this is actually, I guess I went a little bit faster in this class. So this is where we stopped in the morning class, so I don't want to get further ahead or get off sync between the two classes. Is there any questions for me? Maybe I'll show you an example of Exergy in research. So here's an example of them looking at efficiency limits for an internal combustion engine. Okay, so this is, we have the Exergy balance. So if we look at what's going on inside a combustion engine, we have the first law energy balance, right? We have fuel, and then where all that fuel energy ends up going, it's showing you the flow of it here, okay? We could also look at it though, and this is the second law, and they look at it here, it's Exergy or work potential that's occurring from all these energy transfers. And setting up basically Exergy balance right here, they're using it with the term availability, so that's why you see the A, okay, but that's still Exergy, same. That's why you see this A, so it's Exergy or availability. So they have, again, for conservation energy, entropy balance, and then here's where you see the Exergy balance. And they start going through all these subsystems and look at where there's where things could potentially be improved. Okay, so they start talking about different locations because of this. Okay, and you can go through this if you're interested, but this is, I just wanted to give you an example of, here's kind of summarizing it for an engine, looking at the energy balance of where energy is going, and then where the entropy, or sorry, where the exergy is going. Okay. Versus thinking about that you could use 100% of that heat from the fuel. You can't because of the irreversibilities. Right? Okay, so here they start talking about strategies of what now it helps point and say, okay, here's places we can improve, okay, instead of those other places. All right, so that's it. Any questions? Otherwise, that's it for today. All right, well, you guys were a little quiet today, but that's okay. If you have questions, please ask, and don't be afraid to ask some questions or talk to me after class, or we'll set up a Zoom and talk. Okay. All right. You guys have a good rest of your day, and I'll see you on Wednesday.
Thank you, sir. Have a good day.